Do you know the game? It's add, divide and remainder, and we will play this game in this video. Remember the sequence: add, divide and remainder. Like every game has a set of elements which decides its structure and gameplay, we will have a set of elements here, and the elements are, I'll write 0, 1, 2 up to n minus 1. And what is n here? N is a natural number, and this set has a special name. This set has the name Zn, and the game we are going to play, that also has a special symbol. The symbol is add and divide by this n, and this has a name. Name is addition modulo n, and it is defined as I have said, for any two elements, this addition modulo n will give the remainder when a plus b is divided by n. I have to be louder because I was lower in my previous video. My sound was lower. So this is a set, and the game we are going to play is the addition modulo n, and the elements, the players are from this set, and we will get what? The remainder when a plus b is divided by the natural number n. For example, suppose we have z4. Suppose n is 4. We will have the set of elements 0, 1, 2, 3. The elements are possible remainders you will get when you will divide any integer with the number 4. Here also that. Take any integer. The remainder you will get when you will divide that integer by the n. You will get 0 to n minus 1. So these are the possible remainders when any integer is divided by the number n. And suppose I am taking the element 2, 1, 3 and applying the game add, divide, remainder, ADR, this is 4. I will get 2 plus 3 is 5, and 5 divided by 4 is, it will give remainder 1, because 2 plus 3 is 5, and when 5 is divided by 4 we will get quotient 1 and remainder 1. This is our remainder. So we know how to operate any two elements of this set under this operation, and we'll show this is indeed a group. It will form a group, and this group has a special name. This group is called group of integers modulo n. Let me put a underline it. So for the moment we are clear what our set is. Zn. Zn contains all numbers 0 up to n minus 1, 0, 1, 2 up to n minus 1. Like in Z4 we have 0, 1, 2 up to 3. The possible remainders we will get when any integer is divided by 4. We will get 0, 1, 2 up to 3, and the addition modulo 4, when it will be operated with 2 and 3, it will give 1, and when I will operate this addition modulo 4 with 1 and 2, I will get 3. 1 plus 2 is 3. Add, divide, quotient is 0, and remainder is 3. So this is 3. And for any two elements we can operate this operation, and we will get a remainder, and we will show that it is indeed a group. Let me erase the example. For this happy little group, we will use a happy little algorithm to show this is a group. We have a happy little algorithm. We have a happy little algorithm, and the name of that algorithm is division algorithm. Division algorithm. And this algorithm states, for any integer m and for any natural number small n, there exists a quotient q and remainder r, such that m equals to nq plus r, and this r lies between 0 to n, and q, this q and r are q belongs to natural, all these are integers. We'll keep this happy little algorithm in a cloud so that it will not be disturbed. And throughout proving this this set under this operation a group, we will use this algorithm, happy little algorithm, and you know this algorithm very well. For any integer and any natural number, when I will divide that integer by the natural number, I will get a quotient and I will get a remainder, and remainder lies between 0 to n, 0, 1, 2 up to n minus 1. This is strictly less than 1, strictly less than n, and m is n times quotient q plus r, and we will use this division algorithm. First, to show a group, we will show closure, associativity, identity, existence of identity, and existence of inverse of every element. Our set is Zn, this is our set, and this is our operation. First one is closure. Closure. Take any two elements of the set Zn. We'll show that those two elements, when they will be operated by this addition modulo n, the result you will get, that will also lie in this set. For any small a, small b, two happy little elements of this happy little set Zn, by division algorithm. Division algorithm says we have q and r belongs to the set of integers, such that a plus b is equal to n times q plus r, and r lies between 0 to n minus 1, this is strictly less than n, and r is the remainder, and we have This R is nothing but the result you will get when you will operate A with B under this operation addition modulo n, and by division algorithm you have what? R lies between 0 to n, so R equals to 0 or 1 up to n minus 1. R is any one of these elements, and clearly this element belongs to Zn, and this belongs to Zn. Therefore, the set under addition modulo n is closed. Pause the video to note. Now I will erase. Let me erase the closure part. See, we have used this happy little algorithm, division algorithm. Now the second axiom of groups, that is associativity. Let me use the red color, pink color. Associativity will take three elements from the set Zn. For any three elements A, B, C of the set Zn, let us write what we have to show. We have to show that A and B operated with the addition modulo n first, then the result you are getting, that will be operated with the C element under the operation addition modulo n, and that will be equal to, keep A, first operate A and C with our operation, then with A you will get the same result. We have to show this. See, we will use this happy little algorithm again and again in this associativity. Let us see what this one is and this one is. Let us see. By division algorithm, let me use another color. By division algorithm, we have small q1, small r1, such that A plus B is equals to n times this quotient q1 and this little remainder r1, and r1 lies between 0 up to n minus 1. This is strictly less than 1, strictly less than n. So r1 is 0 or 1 or 2 up to n minus 1. By division algorithm we have, this is an integer. Division algorithm says for any integer, for any natural number, you have q and r which satisfies this. A and B are the elements of Zn. A and B are integers, and we are adding them. The result I will get, that is also an integer. And by division algorithm we have q1 r1 which states this. So what is A and B operated with addition modulo n? This is r1, the remainder. So we have this one as r1. Now we will operate r1 with C under the operation addition modulo n. We will again apply by division algorithm. We have q2, the second quotient, and another remainder r2, such that A plus this is R1 plus C equals to NQ2 plus R2, and R2 lies between 0 to n minus 1, this is strictly less than n, and we have when R1 operated with C under the addition modulo n, this is R2 because you are getting the remainder R2, and we have added R1 plus C, add, divide by n, you will get remainder R2. So R1 C operated with addition modulo n, you are getting R2. Let me name this 1, this is 2, this one is 2, and let us erase first 2 lines of associativity, because we are running out of our green board. Now add 1 and 2, add 1 and 2, we'll get, first one is this one, first equation, this is second equation. We'll get, in left hand side we have A plus B and R1 plus C with addition. Write C first, then R1, A plus B plus R1 plus C, A plus B plus C plus R1. In right side we have NQ1 plus R, NQ2 plus R1 plus R2, NQ2 plus R2, this is NQ1 plus NQ1, NQ2 and R1 plus R2. From left side and right side we have R1, I can cancel R1 and R2. Now we have A plus B plus C is n times Q1, Q2 plus R2, and keep R2 one side. R2 is what? R2 is A plus B plus C minus n Q1. Now I will erase. Try to pause the video and note the things. So R2 is what? R2 is, we have R2 equals to this is our R2, and we have got R2 equals to A plus B plus C minus n Q1 plus Q2 in bracket. What we have to show in associativity here, we have to show this one equals to this one, and this one we have got R2, and for this one also we will use our happy little algorithm, the division algorithm. By division algorithm, we will operate B and C first with our operation. So by division algorithm we have Q3 and R3. Let me write here, R3 varies from 0 to n minus 1, strictly less than n, 0, 1, 2 up to n minus 1, and B plus C equals to NQ3 plus R3 with R3 is our remainder. So this is R3. Again we will use division algorithm. once more by division algorithm. We have, see, R3 is this one is R3. We'll operate R3 with A with R3. We have Q4 R4 such that with R4 varies from 0 up to n minus 1, strictly less than n, and R3, I will take A first. A plus R3, these are also in, A is an integer, R3 is an integer, so A plus R3 is also an integer, and this is equals to NQ4 plus R4, where R3 A plus addition modulo n with R3 is R4, because R4 is the remainder here. Let us, this equation give a name 3 and this equation is 4. Pause the video to note. I will erase. Now what we have, we will again do the same procedure. So we will add 3 and 4, add 3 and 4. Let us separate this one. We have in the left side B plus C, right side A plus R3, B plus C plus A plus R3, and in right hand side we have NQ3 plus R3, and this is NQ4 plus R4, and from both sides we can cancel R3. So we have, this is A plus B plus C, R3 will cancel this, and this is N times Q3 plus Q4 plus R4. So we have R4 equals to A plus B plus C minus NQ3 plus, we have R2 equals to, this one as R2, this one is R2. Now R4 is this one. We have R4 equals to the right hand side and previously we had R2 equals to A plus B plus C minus N Q2 plus Q3, Q1 plus Q2, and by these two equations, let us name this. This is as, this was our first one. This is 5 and this is 6. We'll erase this one. So by 5 and 6, let us subtract. Let us subtract 6 from 5, and now we have R2 minus R4 is equals to, this one will subtract 6 from 5, 6 from 5. This one will be subtracted from this one. So this is R4 minus R2. And in right hand side, A plus B plus C, we have in both the equation and they will be cancelled. This one is subtracted from this one. So we have N Q1 plus Q2 minus this one N Q3 plus Q2. We'll subtract 6 from 5. In right hand side of 6 we have a plus b plus c, here also a plus b plus c, they will be cancelled, and this is when subtracted we will have positive nq1 plus q2, and this is minus nq3 plus q4. So we have r4 minus r2 is this one. And now let me erase. Remember, this is r2 and this is r4. So we have n times q1 plus q2 minus q3 minus q4. R4 minus R2 is a multiple of n. Let us note it. Note R4 minus R2, a multiple of n. And what are multiples of n? Multiples of n are either 0 or n, 1 times n, or 2 times n, or 3 times n, so on in positive side. In negative side we have minus n or minus 2n, and so on. So these are the choices for R4 minus R2. R4 minus R2 can be any one of these numbers, and remember R2 and R4 are reminders. We have R2 and R4 numbers between 0 to n. This is strictly less than n. R2 and R4 can be 0, 1, 2 up to n minus 1. So R2 minus R4 can at most be n minus 1, and minus n plus 1, this is minus n. See, R2 and R4 are the numbers between 0 to n. Therefore, their difference lies between minus n to n, because R2 and R4 are less than n and bigger than 0. If you will subtract R2 and R4, you will never get bigger than the number n and less than the number minus n. Therefore, R2 minus R4 lies between minus n to n, and between minus n and n strictly we have only one number 0. So the only choice for R2 minus R4 is 0. That implies R2 is same as R4, and this is R2, this is R4. Therefore associativity holds, and we have this happy little axiom which is satisfied. And next we will jump to identity. Pause the video to note. Now let me erase. See, we have many lines here to show associativity, but the steps are easy. If you have noted, please go on the lines and you will see the associativity, the logic we have used are very simple. Now we have identity. Let me use the pink color. Identity. Identity. See, we have 0 in the set of Zn, and 0 plus any element of this set Zn with our operation addition modulo n. This is A, because 0 plus A is A, and when A will be divided by n, I will get A back, because A is a number between 0 to n minus 1. And on the other side we also have this one as A. So 0 will act as identity of this set under this operation addition modulo n. Next we have inverses. For any A, and this happens for all A in the set Zn. For any A in the set Zn, we have n minus A also an element of Zn. A is a number between 0 to n minus 1, 0, 1, 2 up to n minus 1. A is a number, any one of these numbers. So n minus A also a number between 0, 1, 2 up to n minus 1. And we have n plus n minus A plus n minus A is n. And then we will divide n with the n. I will get remainder 0. So A, when operated with n minus A under the operation addition modulo n, will get our identity 0. Hence every element of this set has inverses, and we are done. And moreover, this set under this operation is also commutative, and this is an abelian group. Let me write it. Pause the video to note. Commutativity will also hold. Commutativity, because A plus B is same as B plus A for any two integers A and B, and when this number will be divided by n, the remainder I will get is the same as when this number will be divided by n. So for all elements of our set Zn, so this is not only a group, it is an abelian group or commutative group. So this happy little set under this happy little operation will form an abelian group, and we are happy. Thank you.